All right, now we can start. Welcome everyone. My name is Valtteri. I'm a developer at Xiphera and your host for today's webinar. For our returning viewers and friends, Xiphera as a company is already well known, but let me briefly introduce our company. We are a Finnish company founded in 2017. We design hardware-based security solutions using standardized cryptographic algorithms, and we offer our implementation of those algorithms as intellectual property cores or IP cores. Our product offering includes cryptographic algorithms and protocols. And furthermore, we design our IP cores mainly for field programmable gate arrays or FPGAs. But our offerings can also be integrated into ASIC and SoC systems. You can always check our website, xiphera.com, for more information about our offerings after the webinar. And if the upcoming presentation raises any questions, small or large, please submit them to the Q&A box that you can find close to the chat icon. We will have a Q&A session after the presentation. And for your information, this webinar is being recorded and can be found from our website within a couple of days. And let's move to the actual agenda of today. And let me introduce to our webinar speaker, Perttu Saarela, who has been working at Xiphera as a PQC expert and has been focusing his research on all PQC algorithms and their side channel attacks and protections this year. Perttu has a strong background in mathematics and information security, and despite his young age, he has already started his academic publication activities on these topics. Please, Perttu, go ahead.
Thank you, Valtteri, and welcome everyone on my behalf as well. We will be talking today about the state of PQC and the upcoming standards, and hopefully building some intuition on the foundations of how these new algorithms are built. So our agenda today will be first defining what PQC is, or what post-quantum cryptography is, and some other basic definitions that we need along the talk. Then we move on to the main part of the talk, which is the foundations of the new standards. We will encounter some minimal math, but we'll keep it light and mostly focus on the intuition of why this is going to be secure. And lastly, we're going to talk about securely implementing these into actual products and devices and how that should be done. And we'll discuss what's known as the hybrid model. Okay, so firstly, some key definitions. These might be familiar to most of you, but let's go over them anyway. So very broadly, encryption can be divided into two families. We have symmetric encryption and asymmetric encryption. In symmetric encryption, Alice and Bob here have some shared secret that they've agreed upon beforehand, before the communication can happen. And once they have the known or shared secret key, they can use it for like bulk communication. And AES is a good example of this. And then what we'll be mostly focusing on today is asymmetric encryption, where we have this private public key pair, where the public key is derivable from the secret key, but it does not go in the other direction. So the secret key or the private key cannot be computed feasibly from the public key. And then the public key is public, so it can be shared around as much as one likes. And this kind of communication is used in exchanging keys and in signature schemes. And The common examples from this are elliptic curve cryptography and RSA, as well as most, if not all, PQC algorithms. At least all PQC algorithms that we will be talking about are in the realm of asymmetric encryption. So let's look more closely at asymmetric encryption. And here we have two types of ideas in this realm, and these are going to be the main ones that we need for the new standards that we'll be talking about later. So firstly, we have key encapsulations or key encapsulation mechanisms. And this is used for exchanging the keys. So here on the left, if Bob wants to establish some shared secret with Alice, he then first decides on the secret to be shared and then uses Alice's public key to encapsulate it, which is essentially encrypting it, but call it encapsulation, and then sends this encapsulated to be shared secret to Alice, where Alice can decapsulate it using her own private key. And then they have the shared secret and they can start the symmetric communication. And then almost similarly, we have the digital signatures where Alice wants to convince Bob of the authenticity of the message or who is actually sending it. And so she signs the message with her own private key such that it is verifiable with her public key. And this public key can be shared around and everyone can just get it. Then to the main definitions of post-quantum crypto. So firstly, why is post-quantum crypto? And that is because of the quantum threat. So the Shor's algorithm is capable of factoring integers fast and solving the discrete logarithm. And what this means is that RSA and ECC can be broken with a quantum computer of sufficiently large computational capacity. And thus we need new types of public key or asymmetric algorithms based on different hard problems than integer factorization and the discrete logarithm. It should be noted here that quantum computers capable of running these attacks do not exist yet, but we still need to take this threat seriously and try to develop these methods as soon as possible. And another important note is that symmetric encryption is not in danger. There is some speed up with quantum computers, but this speed up can be mitigated by essentially eventually doubling key length in symmetric encryption. So here we have the definition of the PQC, that is cryptography that isn't broken by quantum computers. And here again, we note that it is not equal to quantum cryptography, which would be doing cryptography using quantum mechanical phenomena. The point of PQC is that we're able to do this with our classical devices, so laptops that everyone have, and that we do not need any quantum capabilities from our computers. And although PQC as a field is huge, we'll take a look at the algorithms that we'll actually be seeing in the future. So algorithms that will be standardized. And on that note, we'll talk about the NIST PQC competition. So the US-based National Institute of Standards and Technology started a competition-like process for standardizing PQC algorithms back in 2016. For round one, there was 69 algorithms selected, and they were chipped down to 7 finalists and 8 alternates for round 3. The alternates were promising algorithms, but they had some downsides compared to the finalists. And finally, in the summer of this year, we had 4 winner algorithms selected to be standardized. And this standardization process will be starting, and we'll be getting new standards in a couple of years, hopefully. And additionally to the selected winners, the NIST also announced an extra round 4, which also contains 4 new algorithms. And even outside of that, they announced a separate call for new signature algorithms. And the need for these new or extra rounds and new calls for papers will become apparent soon enough. But after these extra rounds, we will probably be getting some additional standards. And then let's look at what actually won round 3 and what went to round 4. So for round 3, the winners that are actually going to be standardized in a couple of years, we have 1 key encapsulation mechanism and 3 signatures. And here, as we can see, we have 3 lattice-based solutions and 1 hash-based solution. So this is kind of what inspired NIST to run extra rounds to try to find different solutions not based on lattices, so that we don't put our eggs all in one basket. And here the Xiphera is probably, well, it's the only key encapsulation, but for the signatures, the main signature will be the dilithium. And then on round 4, we have mainly code-based solutions. We had 1 non-code-based solution, but this was actually eventually broken this summer. And more on that later. And out of these code-based solutions, at least 1 from Bike and HQC will be selected, and Macaleese will see what happens with that. So now we'll move on to the meat and potatoes of the talk, and we'll give some intuition to these 4 types of algorithms that we saw on last slide. So lattices, codes, hash-based solutions, and isogeny-based. And first up, and probably the most important one, is lattices. So here we see a simple example of a 2-dimensional lattice. Lattices have a lot of robust theory connecting to different branches of mathematics, but we'll talk about simple examples here. So this is a 2-dimensional lattice, and the A1 and A2 vectors that we see here are called the basis vectors. So any integer multiple and combination of these vectors will be a point on the lattice. So for example, taking integer multiples of A1 gives us the diagonal line from the bottom left to top right, and taking integer multiples of A2 gives a line perpendicular to that. And then taking any combination of these integer multiples gives us the remainder of the lattice. And to remind you quickly, so the 3 solutions, Xiphera, dilithium, and Falcon, were all based on these lattices, and these are the ones that are going to be standardized. Putting a little bit more rigor to the picture, we can construct what is known as the generator matrix, which is denoted by A here, which is going to be just a matrix with these basis vectors as the columns of the matrix. And then the generator matrix eats up an integer vector and spits out a point on the lattice. And again, this is a 2-dimensional example. In reality, the lattices that are involved in the actual algorithms are going to be hundreds of dimensionals. Okay, so to do this kind of cryptography, we first need a mathematical concept, then we need some hard problem on it, and then we need to know how to do crypto with it. So now we have the concept of a lattice, and then we introduce a hard problem called the learning with errors. And here again, Xiphera and dilithium are both based on learning with errors. And the problem here is that, or we have a problem instance of a generator matrix of a lattice and a secret integer vector. And then we construct this challenge point T by adding some randomly sampled integer noise to the secret lattice point AS. And then we have constructed the challenge. And the learning with errors problem simply asks you that if you're giving a generator matrix and a challenge, can you find the secret vector S? Or can you find the secret lattice point? And this is hard. To demonstrate this, we again have the same lattice as before, and now I've added 3 randomly sampled challenge points. And somewhere in this picture, there is hidden a secret lattice point that is my key in this 2-dimensional toy example. And looking around, it might be difficult to guess where it is. It's here. If you guessed correctly, congratulations. You might be better than a quantum computer. But here, we briefly demonstrated how the challenges are constructed from the secret point. But again, this is a very simple toy example that is easily visualizable in the 2D-dimensional case. In reality, we'll be dealing with hundreds of dimensions. And how do we do cryptography with this is, well, not simple, but we're fairly straightforward. This slide might be a bit busy, but let's only look at the key points here. So the public key is going to be a learning with errors instance. So a generator matrix and a challenge. And the private key is going to be the secret vector. And then when we want to encrypt a message, we construct from the message an integer vector and then find or generate the corresponding lattice point. And then we also multiply this message vector with our challenge vector and add some randomly sampled noise. And then the decryption is nothing but taking this noisy component of the ciphertext and subtracting from that the message point multiplied with our secret. And if we have a decoding procedure that can get rid of the noise, we are left with our original message. And then here we have only talked about integer lattices, but in reality, the schemes are based on different variants where integers are replaced with polynomials or vectors and matrices of polynomials with some criteria. And these are known as ring learning with error and module learning with error. Then moving out from lattices and on to codes. And when we say code-based, we mean that they're based on linear codes. And here we were talking or saw that in round 4, we have 3 of these HQC, Bike, and Macaleese, and at least one of them will be standardized. Codes are nothing more than a way to add redundancy to a message. So we take a message vector and then we multiply it with a generator matrix and get a code word of the particular code. Why do we want to do this? Well, there's lots of cases, but probably the most useful part of this is error correction. But these linear codes are widely used outside of cryptography. Many of you might have heard of them before, examples like Reed-Solomon and Reed-Muller and Hamming codes, and they're used in communications and data storage. And one example is QR codes. If you haven't heard of them, a very simple example of this would be a binary vector of any length, and then we extend it by 1 bit by computing the checksum or just XORing every bit together and adding it to the end. So in that case, if 1 bit were to be flipped, we would notice that the checksum doesn't match anymore. And here we can see kind of a parallel to the lattices that we again have some vector and a generator matrix, and that gives us another vector. But in the case of lattices, the generator matrix was a square, and now it is more wide than it's tall. And this G gives the codage properties. And as said, linear codes are used as error correcting codes. So where some errors to happen in the code words, some say T amount, then a particular code could be able to decode properly even in the presence of that amount of errors. Okay, so now we have the concept of linear codes, and the hard problem will be what's known as syndrome decoding. Defining syndrome decoding rigorously takes a lot of notation and dry maths, so I'll just verbally briefly explain it. So syndrome decoding requires finding certain types of code words with a fixed amount of non-zero components. And to say that this is hard in even more simple terms is that finding code words with some desired properties can be very difficult. And it is that syndrome decoding is hard, and indeed NP hard if talking about complexities. And now that we have the hard problem, we can build the crypto system on top of it, in which in code-based crypto, the public key will be, again, generator matrix of some known code. The code to be used is kept public data. And then we have a secret key, which is going to be a decoder or decoding procedure from a code word back to the message such that it can correct up to T errors. And then the encryption of a message is nothing but mapping the message to a code word and again adding some randomly sampled errors such that this error vector has T errors in it. And then when we feed this to the decoder in the decryption process, the decoder can correct up to T errors. So out of this, we get the original message M. Yes. And then we'll move on to the hash-based schemes. So when we talk about hash-based schemes, we're precisely talking about hash-based signatures, which in a nutshell are that we do a huge amount of hashing with some complicated data structure. And what's this all built from is what's known as one-time signatures. So we'll talk our way through this picture here on the right. So the one-time signatures are going to be the squares on each level. So let's look at the bottommost level here. So the one-time signature is going to be a public-private key pair or using the signature, and that's what's stored in here. And when we want to sign a message, we use this message and hash with the keyed hash functions together with the public key using the private key multiple times. And then we get a signatures, and the signature is designed that you can compute the public key out of it using the message. And then the verifier can check that that public key is indeed your public key. Then moving on from that, we get to, we're mentioning that these one-time signatures can only be used once, as the name suggests. So if you use the same public key, private key pair, you're going to leak some information about the private key, and that's a bad thing. So we want to extend the usage of this scheme by having multiple different key pairs. And we do this by constructing a Merkle tree. So let's now look at the topmost tree here. So in this, the squares are again the one-time signatures with distinct key pairs. So now we have this many signatures that we can do, and the public key has now become the root node of this tree. So to sign a message, you sign it like you did before in this level, but then you hash up the tree, meaning that you get the upper node by hashing it with the neighbor, marked in orange here. So going from this root to this node to the root node, we hash together with this node to get the one above, and then we hash together with this node to get the one above, and then hash together with this to get the public key. So the signature will now be the signature given by this one-time signature and the necessary nodes for the computation of the public key. And finally, to get even more signs out of a single tree structure, we combine these Merkle trees into a tree of trees, so a hypertree. And that's how we get this entire structure. And the key here is that the bottom layer is used for signing messages, and the layers above are used for signing the public keys of the trees below. And it should be mentioned that there are two types of hash-based signatures. There's stateful and there's stateless. The stateful is when the tree needs to keep track of many things at once, and these might be inconvenient for personal use, and it is not recommended in that case, but even NIST is recommended a few standards of stateful versions for those who are in a hurry to get PQC algorithms before the standardization process is ready. And the PQC Sphinx that is going to be standardized is a stateless version of this, where the structure gets even more complicated. And lastly, and this case leastly, is the isogeny-based schemes. There was one contender in round 4 called Psych, which is super singular isogeny key encapsulation. And this just builds on top of elliptic curve crypto such that we get these maps between different elliptic curves. So isogeny is a math term referring to a certain type of map between two elliptic curves such that you preserve a certain property. But Psych was unfortunately broken during the summer, and not just broken, but completely obliterated, in the sense that you were able to break it with a laptop in a couple of hours. So this does not mean that all isogeny-based crypto is doomed forever, but it casts heavy doubts on these schemes in general. Now we can leave the world of theory behind, take a breather, and move on to some practical considerations. So let's look at some concrete numbers. So here we see some stats for the key encapsulations, and here we have security is the NIST security levels, 1 being the lowest and 5 being the highest. That is to be standardized. And then the lengths of private public keys and ciphertexts are given in bytes. So at the top, we see the pre-quantum ECC schemes with nice and small key sizes and ciphertext. And then looking down, we see that the post-quantum stuff multiplies these key lengths and ciphertext lengths manifold. This does not directly attack like the runtime, but this is going to take a lot of space. The Kyber that we here see is going to be like the main key encapsulation mechanism for now, and we have big keys and ciphertexts, but looking down the list, we see that it could be worse. Lattice being notoriously bad for having huge public keys, although Lattice would have the smallest ciphertexts from PQC algorithms. And we also see that Psych would have been great for having small everything, but it again broke. And here again, the winner Kyber is the one that is going to be standardized soon, and then one from the round 4, at least one from the round 4 algorithms is going to be standardized. Then looking at the signature stats, we again see that the lengths are going to increase. For dilithium and falcon, they're going to increase quite a bit, at least in all categories. And for Sphinx, the private and public key remain relatively small, but the signature sizes are going to be a lot bigger. And Sphinx gets 2 places here for S and F, where S means that it's optimized for size, and F means that it's fast and optimized for speed. And here again, a dilithium is meant as the main algorithm, but then Falcon is meant for devices who may not have as many resources. Okay. Here, so the standards are what we just discussed, and they are coming in a couple of years. And now is a good time to get involved in this. So designing a system that is going to be around for years should be quantum secure. You should have support for some of these PQC standards if you're going to have now build a system that's around for years. And what we've seen from this talk is that these are very maths heavy topics and complicated, and they are very optimized in the implementation sense, and so they are difficult to implement. So one should be very careful in implementing these, as to not leave one open for attacks. And then we've seen these algorithms being broken. So Psych was completely broken, and one round 3 candidate called Rainbow was also broken. So this newness of these algorithms doesn't immediately imply that they're secure. They're secure insofar as we have no reason to assume that they're not, but the security is based on trust, and building this trust is based on years of not being attacked. And here FPGAs give a good platform for this, as they provide some speed up in these complicated operations, but they're also reprogrammable. So if some catastrophic event were to happen, you can replace the algorithm easily with another one. And then to take the step from classical to post-quantum, we have this intermediate step known as the hybrid model. Here we combine the two. So we combine the classical and we combine the post-quantum. And this is the recommended practice of what's going to happen. And it's recommended, for example, by the National Cybersecurity Agency of France, ANSSI. And concretely, this works for key encapsulations. You perform both classical and post-quantum key encapsulation, and then you feed the results combined into a key derivation function, and you get your shared secret. And for documents, you simply just sign the document twice, once with a post-quantum one, once with a classical algorithm. And then verification is just verify both signatures and accept only if both signatures verify true. And here again, we get some advantage from FPGAs that if a system already has some hardware accelerator for a classical algorithm, then an FPGA can be easily added to this system to make it into a hybrid system. And then finally, what's going to happen next? So the first standards are going to be coming out in a couple of years, hopefully. And in the meantime, also round 4 will finish up, and we'll see if we get some new standards as well. And then moving on from the standards, we see that there's a need for some non-lattice-based solution. That's again not to say that lattices are somehow insecure, but in the case that there would be some catastrophic attack on them, we want to have some options available. So there's a lookout for non-lattice-based solutions. So we again have the codes and the hash-based, where we want something more again. And then we have this huge area of ongoing research that again has something to do with the non-lattice-based solutions, but a big part of this is also side channel attacks. So now that we have some secure algorithms, we also want to implement them in a secure way. And what this means is that side channel attacks mean that you observe some leaking information from the implementation. So how long it takes from different inputs and what's the power consumption. And you can measure this data, and if the system is not implemented securely, then this might leak the information and break the system. And this is a big ongoing research part of this area. And then, of course, there are people looking out for glory and trying to find just classical attacks or even quantum attacks against these algorithms to break them. As we've seen, a couple of them have been broken, but who knows what the future will hold. And if you want to see more about side channel attacks, our previous webinar from June was on side channel attacks on the classical side on elliptic curves. And that's it for the talk. Thank you everyone for listening. I hope that you learned something from this.
Thank you, Perttu. So complicated matter was wrapped in a very understandable format, and even the mathematics were clearly simplified, even for me. And now it's time for the questions from the audience. I can see there's quite many questions already in the Q&A box, and if you still have anything to ask about the talk, please submit them now so we can go through them. The first question is a practical one. So if cryptographically relevant quantum computers does not exist yet, why are PQC algorithms relevant already today?
That is an excellent question, and a relevant and a valid question here. So there might be 3 points that we go over. First, this is a bit jokingly said, but there are no cryptographically relevant quantum computers that we know of yet. So, but well, probably they don't exist yet. But then the second point is that we want to have this security in place before these algorithms exist, because being able to break our encryption schemes even momentarily would be a catastrophic event. So we want to have the security in place before the quantum computers are here. And then thirdly, and probably most concerningly, is that there might be some government level entities recording the data stream of today and of these times, and waiting for quantum computers to become available when they can break the encryption on the data that they store now. So having the post-quantum algorithms in place as soon as possible is preferable.
All right, thanks, Perttu. That makes sense. And then we have a question about the mathematical side. So how is the noise generated in the learning with errors problem, and does it have any limitations?
Again, a great question. So in almost all of these schemes, not just the ones based on learning with errors, we need to generate some errors. And there are many ways of many cryptographic primitives used in this. There are extendable output functions and pseudorandom functions and ways to just extract more randomness. But to extract more randomness, we need some initial randomness, which comes from pseudorandom or completely random seed. This could be, for example, generated by an entropy source or a true random number generator. So we give this seed to these generating functions, and they generate the random structures.
All right, of course, cryptography needs randomness. And let's hop on back to the practical side again. So you mentioned the different key lengths and how the key lengths are noticeable bigger than with classical like ECC. So how about the computation speed compared to the ECC of the PQC algorithms?
Yeah, so let's briefly look at the table that we had here before. So firstly, for KEMs, we do indeed see that there's a lot of bigger numbers here in the screen, but the penalties are mostly going to be only on the memory side of things. So computationally, in terms of speed, we don't really lose anything here. And some of these schemes are even a bit faster than what the elliptic curve counterpart would be. And the exact same thing holds here for these signature schemes. So again, there's some lengthening of keys and signatures, but the speed penalty is not going to be noticeable.
All right, thanks again, Perttu. Unfortunately, we are running out of time and cannot answer all of your great questions. So if your question was left without an answer, please don't hesitate to contact us or directly Perttu. We try to answer your question. And you can see the contact information on this slide. And indeed, we have a time for one question, and I'm going to give my expertise answering one question from the audience. And as this was the 4th webinar, there are 3 webinars already available, and those can be consumed from our webpage as a video or downloadable audio format. And as I mentioned, this webinar is also going to be available on the website in a couple of days. And I'm sorry to announce, but this was our last webinar this year. And we are coming back in January, and please stay tuned for the next webinar then. And thank you for tuning in and attending our webinars. See you in January. Bye-bye.